You think you know what time is. Second hand ticks. Minute hand moves. Coffee gets cold. Your phone tracks every single moment from now until you die. But down at the scale of atoms, where electrons orbit nuclei and photons zip through clouds of rubidium, time doesn't just slow or speed up. It stops making sense. It flows backward. It vanishes entirely. University of Toronto, late 2023. A cluttered basement lab packed with aluminum-wrapped devices and carefully calibrated lasers. Daniela Angelo and her team fire photons through ultra-cold atoms. The atoms get excited. The photons pass through. Standard physics. Except when they measure how long the atoms stay excited, the clock reads negative. Not zero. Not near zero. Negative. The photons appear to exit the cloud before they enter. The atoms get excited before the light arrives. What breaks when time itself goes negative? Why do the equations of quantum mechanics erase time completely at the smallest scales? And if time doesn't exist at the atomic level, what are you actually experiencing right now? This script is researched and factual, using sources from the preprint published September 5th, 2024 on archive.org by Angelo and colleagues showing experimental evidence of negative time and photon interactions, and from the December 23rd, 2024 paper in Quantum Studies Mathematics and Foundations by Ridley and Adlam on time and event symmetry in quantum mechanics. Both papers dive deep into territory most physics textbooks avoid. Now back to the information. The electron orbiting the hydrogen atom doesn't experience time. The equation describes how the probability wave changes with respect to time, but the electron itself has no clock. Werner Heisenberg notices this immediately. His uncertainty principle says you can measure position and momentum, but the more precisely you know one, the less you know the other. Energy and time seem similar, except they're not. There's no time operator in quantum mechanics. You can't build a device that measures time the way you measure position. Time is something else, something outside the system. The Hamiltonian constraint acting on the wave function equals zero. No time derivative, no evolution. The wave function of the universe is timeless. It describes all possible configurations of space-time at once, static, frozen, eternal. This is called the problem of time in quantum gravity. If the universe's wave function is timeless, where does our experience of time come from? Why do we remember the past, but not the future? Why does coffee cool but never spontaneously heat back up? After quantization, space-time dissolves. What remains is space, the configuration of all possible three-dimensional geometries. No trajectories, no evolution. Just a static superposition of every possible arrangement of matter and energy that could ever exist. Don Page and William Wooters propose an answer in 1983. Take the timeless Wheeler-DeWitt universe, split it into two parts. One part acts as a clock, the other part is everything else. The clock and the system are entangled, not interacting, just entangled. Quantum correlations link them. Now condition the system's state on the clock showing a particular time. The system appears to evolve. Schrödinger's equation emerges. Time is not a fundamental feature of reality. It's a byproduct of entanglement, a relational property. The system evolves relative to the clock, but from outside, viewing the entire universe, nothing changes. The global state is timeless. This is the Page-Wooters mechanism. The Schrödinger equation with time as a parameter. Take the classical limit of both, and you get Hamilton's equations of motion. Time emerges from entanglement, not as an external background, as a manifestation of quantum correlations between subsystems. The more entangled the clock and system, the more time appears to flow. He demonstrates that you can extend the Page-Wooters mechanism to include space, not just time. Three-dimensional space plus one-dimensional time emerging from a fundamentally timeless and positionless universe. The mechanism reproduces gravitational time dilation. Clocks near massive objects run slower, exactly matching the Schwarzschild solution from general relativity. All from entanglement, no background space-time required. Michael Ridley and Emily Adlam take this further in December 2024. They identify two types of temporal symmetry. Time symmetry, where forward and backward time directions are equivalent, and event symmetry, where all moments in history are treated equally. Existing time-symmetric interpretations of quantum mechanics fail event symmetry. The two-state vector formalism, where quantum states propagate both forward and backward in time, privileges certain moments over others. Ridley and Adlam build on the fixed-point formulation of quantum theory. They define an event as a fixed-point constraint on the Keldysh time contour, a way to mark moments without breaking the symmetry. They show both time and event symmetry can coexist in a multiple time formulation. And all at once, a temporal picture, where the universe doesn't evolve, it just is. Past, present, and future are equally real, or equally unreal. Even with these assumptions, the equations describing the system behave identically whether time moves forward or backward. The memory kernel, a key part of the equation, is symmetric in time. A time discontinuous factor emerges naturally. Unusual because physics equations are continuous, but it keeps the time symmetry intact. The system can support 2 arrows of time simultaneously, one pointing to the future, one to the past. Published in Scientific Reports, Volume 15, Issue 1, Article 3658, on February 13th, 2025. The CPT theorem states that all quantum field theories obeying certain conditions must be CPT invariant. Flip a particle into its antiparticle, mirror its spatial coordinates and reverse time, and the physics looks identical. Individual pieces can break. Parity broke in 1954 when Chien-Shiung Wu showed weak interactions violate left-right symmetry. CP symmetry broke in 1964 when Cronin and Fitch discovered neutral K mesons decay asymmetrically, but CPT holds. Nature doesn't distinguish past from future at the fundamental level. It's about the probabilities of processes and their time-reversed counterparts differing slightly. A neutral B meson decaying to certain particles has a slightly different rate than the reverse process. Measured directly in experiments at particle colliders. The difference is small, but it's real. It's experimental evidence that a photon can spend a negative amount of time in an atom cloud. Ephraim Steinberg, quantum physicist at Toronto, posts on social media. Sounds crazy, I know, but check it out. The experiment took over 2 years to optimize. Lasers calibrated to avoid distorting results. The setup involved shooting photons through a cloud of ultra-cold rubidium-85 atoms. 2 beams, a strong signal beam causing atomic excitations. A weak probe beam measuring phase shifts. When photons pass through the cloud, some get absorbed. The atom jumps to an excited state. Later, it re-emits the photon and drops back to the ground state. Standard atomic physics. A consistent, reproducible result. The group delay, the time it takes for the peak of a light pulse to travel through the medium, is negative. Photons appear to exit before they should. Atoms get excited before the photons arrive. Causality seems inverted. But if you built a quantum clock to measure how long atoms spend in the excited state, the clock hand would move backward rather than forward. Not slightly backward, clearly backward. The measurement is unambiguous. The quantum fuzziness of photons means absorption and re-emission don't happen at a single fixed moment. They occur across a spectrum of durations, some instantaneous, some taking longer, some, bizarrely, negative. When you average over all possible paths the photon could take, you get a negative value. The Independent covers it. BBC Science Focus publishes an explainer in December 2025, saying time might not exist, quoting the Toronto experiments as evidence. Skeptics push back. Some claim it's just a mathematical artifact, an illusion from how group velocity is defined. Steinberg responds that they've made their choice about how to describe the results. The negative time is as real as any other quantum measurement. It's not time travel. No information moves faster than light. But it shows time at the quantum scale behaves nothing like the time we experience. They measure the actual physical duration the atoms spend excited, not just the pulse shape. And that duration is negative, it's not reshaping. It's the atoms themselves existing in a superposition of excited and ground states in a way that, when measured, yields a negative time. It means time as a concept breaks down when you zoom into quantum interactions. The photon interacting with the atom doesn't have a well-defined moment of absorption or emission. Those moments are smeared across probabilities. And probabilities can add up to give you negative durations. If time emerges from entanglement, then measuring time means measuring correlations between subsystems. A photon and an atom are entangled during the interaction. The measurement collapses that entanglement, and the collapsed state can yield values, including negative ones, that violate our classical intuition. A paper in Physical Review Research Volume 6, published September 29th, describes quantum algorithms for parallel in time simulations using the Page-Wouters formalism. Classical time is promoted to the quantum realm by introducing clock qubits entangled with system qubits. You can compute temporal properties over n different times using only log n qubits. Exponential trade-off between time and space. Time becomes a quantum observable, not a background. The entanglement between clock and system qubits encodes information about dynamics. Time is information. You need infinite resources to distinguish between different operations, even if the clock is not ideal. In the pre- and post-selected approach, measurements are described dynamically. The resources of the clock matter. There's a fundamental limit to how precisely you can define time. Quantum clocks have finite resolution. Heisenberg's uncertainty principle for energy and time implies you cannot measure both with arbitrary precision. A clock with limited energy cannot distinguish arbitrarily small time intervals, just existence. Of unexpected quantum behavior, challenging classical notions of temporal progression, not violations of relativity, no faster than light signaling. But evidence that time's arrow, the directionality we experience, is not fundamental. Wouters' construction. They address the challenge that quantum systems like atoms serve as clocks in experiments, but theoretical time remains abstract. They show that clocks can synchronize naturally without interaction in an ideal scenario. But real-world conditions like relative motion disrupt synchronization. The Page-Wooters construction doesn't account for spatial dimensions. Open problem. Attosecond chronoscopy pushes time measurement to the atomic unit of time. 1 atomic unit equals about 24 attoseconds, 2.4 times 10 to the negative 17 seconds. At this scale, you can probe tunneling ionization and photoionization. A paper published on ARG of June 1st, 2024 discusses dependency of quantum timescales on symmetry. Spin-resolved measurements in copper show ionization. Time delays depend on dimensionality of electronic states. 3-dimensional, 2-dimensional, 1-dimensional, 0-dimensional systems behave differently. Symmetry breaking changes quantum timescales. Reduced symmetry increases the time delay. Scales where quantum effects of gravity become important. A paper from June 2025, available on AR Crixev as 2506.12001, examines whether CPT symmetry can emerge dynamically in quantum gravity. Using functional renormalization group techniques applied to asymptotically safe gravity, researchers find CPT violating couplings do not vanish automatically. They can be set to 0 consistently, but there's no dynamical mechanism forcing them to 0. CPT symmetry must be imposed by hand, not emergent, fundamental, or absent. The standard model extension framework developed to test CPT breakdown provides a systematic way to search for tiny deviations. Experiments with antiprotons, antihydrogen, neutral kaons, and B-mesons set stringent limits. The electron-electric dipole moment, if non-zero, would indicate CP violation, and thus T violation assuming CPT holds. Current bounds are incredibly tight, less than 10 to the negative 29 electron centimeters. No signal yet. This all circles back to the question, if time doesn't exist at the fundamental level, what is happening? Events are points with time coordinates, just like space coordinates, nothing special about now. Microscopically, time reversal symmetry holds. Entropy can decrease locally, ice forms in freezers, but globally, averaged over the universe, entropy climbs. That's the arrow of time we experience. But what counts as a measurement? Decoherence. Interaction with the environment. The environment acts like a continuous measuring device, constantly collapsing superpositions that creates the appearance of time's flow. Coherent quantum systems, isolated from the environment, don't experience time that way. They stay in superposition, timeless. The photon atom system is partially isolated, not completely. There's an environment, the probe beam, the measuring apparatus, but during the interaction, the system is in a superposition. The photon absorbed and not absorbed simultaneously. The atom excited and not excited. When you measure, you collapse that superposition. The measurement yields a value for how long the atom was excited. And that value, averaged over many trials, is negative. The system doesn't experience time linearly during the interaction. It experiences a quantum smearing of time. And when that smearing is measured, it can look backward. Your brain states are entangled with photons hitting your retina, with neurons firing, with the position of clock hands. That entanglement structure is what you perceive as time. Moment-to-moment change is correlation structure shifting. Memories are entangled states linking past configurations to present ones. The future is the set of possible entanglement patterns not yet realized. Time is not a thing. It's a relation, a way of describing how different parts of the universe are correlated. When correlations are strong, time appears to flow smoothly. When they're weak or scrambled, time becomes fuzzy. At the quantum level, where entanglement is maximal and superpositions dominate, time dissolves. Events are defined by fixed points on a time contour. Multiple histories coexist. The wave function encompasses all of them. You can derive consistent probabilities for measurements at different times without privileging any particular moment. Published in New Journal of Physics, Volume 25, Article 023027, February 2023. Loop quantum gravity, an approach to quantum gravity using connection variables instead of metrics, also tackles the problem of time. In the loop representation, the Wheeler-DeWitt Equation simplifies. Solutions can be found at least formally. Lee Smolin and Carlo Rovelli developed this in the 1990s. States are described by spin networks, graphs with edges labeled by spins. These spin networks evolve, but not through continuous time. Through discrete transitions, spin foams. Each transition is an event, no background time, just a sequence of quantum events causally related but not embedded in a time dimension. But in the fundamental theory, time might be emergent from string interactions. The world sheet of a string, the two-dimensional surface it sweeps out as it moves through space-time, has its own notion of time, proper time along the string, that's distinct from external time. At high energies, near the Planck scale, this distinction matters. Strings can have multiple time dimensions in their internal dynamics. Projected down to 4 dimensions, we see one time. But fundamentally, time structure is richer. It's telling us that our usual concept of time is not fundamental. It has no physical meaning, only relative phases between different states matter. An isolated atom in a pure energy eigenstate is timeless. The time of the jump is not well defined. It's smeared. And measurements collapse that smear into an outcome, which can be negative. Scale up from atoms to molecules to cells to brains. At each level, decoherence increases. Quantum superpositions collapse faster. The environment measures the system constantly. Time appears more classical. Clocks tick regularly. Memories form. Cause precedes effect. But fundamentally, it's still quantum correlations. Just many of them. Entanglement on a massive scale. Your perception of time flowing is your brain tracking correlations between internal states and external events. The correlations are real. The flow is an interpretation. Time matters for quantum computers, not as a fundamental background, but as a measure of how long the system can stay coherent. Decoherence time, nanoseconds to microseconds for most systems. Quantum error correction extends this, but it's a fight against the environment imposing classical time. Measure one, and the other's state is determined instantly, not faster than light signaling. The information still travels classically, but the correlations are non-local. Bell's theorem and experiments violating Bell inequalities confirm this. Quantum correlations are stronger than any classical correlations. They're what knit space-time together in quantum gravity theories. The universe's wave function, if it's described by the Wheeler-DeWitt Equation, is timeless. But we observe a universe that's expanding. The cosmic microwave background radiation has temperature fluctuations imprinted 13.8 billion years ago. We see galaxies receding. The universe has a history. How do you reconcile that with a timeless wave function? Our measurements select a particular branch of the wave function. That branch has a well-defined history, a sequence of events we interpret as time. But other branches, other histories, also exist in the wave function. Parallel universes, the many worlds interpretation. Each measurement branches the universe into multiple copies, one for each outcome. Each branch experiences its own time. Globally, across all branches, the wave function is timeless. Time is branch-specific. Even though the Wheeler-DeWitt Equation doesn't have explicit time, you can recover time evolution by treating the scale factor as a clock. This is the Born-Oppenheimer approach applied to cosmology. Separate the degrees of freedom into fast and slow. The slow ones act as a clock for the fast ones. Space-time as a classical background, not quantized. Quantum fields propagate on this background. Hawking radiation from black holes emerges from this. Virtual particle pairs near the event horizon. One falls in, one escapes. The black hole emits radiation and loses mass. Time matters here. The horizon's location changes as the black hole evaporates. But the quantum fields themselves are described by commutation relations that don't privilege a particular time coordinate. Different observers, splitting space-time into space and time differently, see different particle content. Vacuum for one observer is filled with particles for another. Time is observer-dependent even at the quantum field level. 10 to the negative 44 seconds. Below this, quantum fluctuations of space-time become important. Wheeler called this quantum foam. Causal order becomes fuzzy. Quantum superpositions of different causal structures. Events don't have a definite order. We perceive a sequence because memories create a sense of continuity. Time is a story we tell ourselves. This is not about many particles. It's not about entropy or thermodynamics. It's about the fundamental quantum behavior of light and matter. And that behavior includes negative time, not as an emergent property, as a direct consequence of the probabilistic nature of quantum mechanics. The photon's path through the atom is not a single definite path. It's a superposition of paths. Average over them, and you get negative time. That's the quantum reality. Have a negative value. And that value is not a mathematical trick. It corresponds to something physical. The phase shift of the probe beam, the change in the atom's state, real measurements yielding real numbers, numbers that happen to be negative. Understanding photon-atom interactions is crucial for quantum memory, but that's speculative. Time at the atomic level is not what we experience. Quantum mechanics erases time in fundamental equations. The Wheeler-DeWitt equation is timeless. The Page-Wooters mechanism shows time emerges from entanglement. The Toronto experiment demonstrates time can be negative. All pieces of the same puzzle. Time is not a river flowing from past to future. It's a structure built from quantum correlations. If you're still thinking of time as a universal clock, quantum mechanics is telling you to stop. There is no universal clock. There are only subsystems correlated with each other. That web of correlations is your experience of time. The structure of that entanglement is what we perceive as the universe evolving through time. Change is the rearrangement of entanglement. The wave function is static, and we experience different slices as different moments. If time is not fundamental, causality might not be either. Quantum mechanics challenges causality with delayed choice experiments. The double slit with a detector inserted after the particle passes. The particle's behavior changes. Quantum correlations span space-time. Physicists working on emergent space-time scenarios like ER equals EPR, equating wormholes with entanglement, take this seriously. A wormhole in general relativity connects two distant points in space-time, an Einstein-Rosen bridge. Traversing it is time travel to a different location. But Juan Maldacena and Leonard Susskind proposed wormholes are quantum entanglement. Entangled black holes are connected by a wormhole. The geometry of space-time is the geometry of entanglement. Time is a dimension in that geometry, but the geometry itself comes from quantum information. Bits, qubits, entanglement, entropy. Time, being part of space-time, is also generated by entanglement. No entanglement, no time. Our body with the environment with the rest of the universe. That chain of entanglement is what we call time, but not absolutely. Either way, it's new territory. If all moments in history are equivalent, then memory is not access to the past. It's a correlation structure encoding past configurations. Forgetting is loss of correlation. Remembering is reconstructing correlation. Your sense of self, continuous over time, is a correlation pattern. Break the pattern, and the self fragments. This touches philosophy of mind, personal identity. What makes you the same person from one moment to the next? Not a soul, not a substance, a pattern, a structure of correlations. Time is the framework organizing that structure, real and emergent. We impose time on it to make sense of our experience. But the universe doesn't need our time, it just is. This works for macroscopic systems, gases, stars, galaxies. But for small systems, quantum systems, entropy fluctuates. Time direction fluctuates. Negative time is a local entropy decrease, allowed by quantum mechanics, forbidden macroscopically. But the photon was transmitted, not absorbed and re-emitted. It's a superposition. Both happened and didn't happen. The measurement collapses it to one outcome. That outcome includes a negative duration. Entropy went negative locally. Time went negative. Thermodynamics allows it for brief moments. Quantum mechanics measures it. The Page-Wouters mechanism says time emerges from entanglement. The Toronto experiment says time can be negative. The CPT theorem says time reversal is a fundamental symmetry. The second law of thermodynamics says entropy increases, giving time a direction. String theory and loop quantum gravity say time emerges from more fundamental structures. Particles, fields, wave functions do not evolve through time. They exist in a timeless configuration. What we call time is a pattern in that configuration, a way of organizing correlations. Entanglement provides the structure, entropy provides the direction, measurement provides the moments. And at the smallest scales, where quantum effects dominate, that pattern includes backward moments, timeless states, and durations that defy classical sense. You are not moving through time. You are a pattern of correlations embedded in a larger pattern. Your experience of now is the structure of correlations at this slice of configuration space. Your memory of the past is a correlation linking this slice to another. Your anticipation of the future is a correlation linking this slice to potential others. The linking is not temporal, it's quantum, probabilistic, timeless. In late 2023, the Toronto lab measured atomic excitation time. Photons passed through rubidium. Atoms got excited. Time went negative. They repeated the experiment dozens of times, same result. They published in September 2024 on arXiv, Article 2.409.03680, peer review ongoing. The result stands. Daniela Angulo led the measurements. Kyle Thompson, Vita Michelle Nixon, Andy Zhao assisted. Ephraim Steinberg supervised. Howard Wiseman provided theory. They used the cross-Kerr effect, measuring phase shifts in a probe beam caused by atomic polarization. The phase shift is proportional to the time the atoms spend excited. That time came out negative, consistently, measurably, undeniably, in the quantum sense of what a clock measures, backward. The photon exited before it entered. The atom was excited before the photon arrived. Causality inverted at the quantum level, for a duration measured in attoseconds, but negative nonetheless. And fundamentally, not flowing, just existing, timelessly. Or if time exists, it exists only in the correlations between subsystems. Take away the correlations, and you take away time. Leave only the wave function, static, eternal, timeless. Not the way you experience it. What exists is quantum correlation. Entanglement, superposition, measurement. And when you measure time in a quantum system, you might get a negative answer,